This video is for the fastest revision of mechanical operation for gate as well as semester exam purpose. So in case you want to learn the concepts in detail, I think you should move to a different video, but this is meant for only revision purpose, and so it will be the fastest instead of the videos that are on YouTube which are of 1 hour 2 hour. So let's start. First, what is sphericity? Sphericity is the surface area of the sphere to the surface area of the particle, in which the volume of the particle is equal to the volume of the sphere. What I mean here is the formula that finally we end up with is sphericity is equal to 6 by dp. The dp is diameter particle and sp upon vp. This is the formula, and one way to remember it, that volume of the particle is equal to volume of sphere, and volume of sphere is pi by 6 dp cube. So in this we can find out dp and put it and finally get the sphericity. Now there is one more thing, that is surface shape factor. Surface shape factor, which is nothing but the reciprocal of sphericity. Next we move on to one basic common thing, that mostly we have coarse particle, then fine particle, then very fine, and then ultra fine. These are mostly in the ranges of, this in the range of inch or centimeter, this in millimeter, this in micrometer, and finally nanometer. This is one thing, that way we can find out which particle is in which range. Now next thing is the different laws. We have first the Rittinger's law, which is nothing that it gives that the power upon the mass flow rate is nothing but kr, the Rittinger's constant, and 1 upon dB minus 1 upon dA. Here dB is product diameter, which would be obviously less, so this quantity will be more, and dA is the feed diameter. So this is Rittinger's law. Next we have, the first is the Rittinger's law, then came Kick's law, and in Kick's law we take the ln, so it's kk, and we take the ln. So log of obviously dA upon dB, because log should be positive, so upper term should be more, so dA upon dB, and kk is Kick's constant. This is the same power upon the mass flow rate. Finally we have the Bond's law, that is the most used, and in Bond's law it is P by M is equal to KB and 1 upon under root dB minus 1 upon under root dA. And here this KB is the bond constant, and one thing to note is that this KB is nothing but 0.3162 into work index. Okay, work index is nothing but the amount of the energy required to actually crush the very large particle, that means infinite size particle, to at least 80% of that should pass through 100 micrometer screen. Okay, that means 80% passing means the to a size of 100 micrometer from infinite diameter. This is the formula. And one also main thing is Rittinger's number, which is nothing but 1 upon Rittinger's constant. Next there are some minor formulas, such as the specific surface area. So ASS is 6 by phi rho summation of xi upon dpi. Now how to remember it is that if we know phi is equal to 6 by dp upon, let's say this is our area, this is S upon V. So what we can put V as, we can put V as mass upon density. So sphericity 6 by dp upon s upon mass upon density. So this goes up here, let's say s goes up here, so 6 by dp, and we have here sphericity comes down and mass also comes down, mass goes up and density comes here. Okay, so we have a similar term, this mass and dp, this is by dp, so dp comes over here, and what we can see, if we divide by total mass, this would be xi. So similar thing that I have written, that ass, the formula is ass is 6 by phi rho summation. Now we need to sum of different fractions by dpi. Next there is arithmetic diameter dn, which is the summation of number, n denotes number of particles with diameter dpi and by total number. Also we have mass mean diameter, that is xi dpi, mass fraction into dpi. Then we have volume, based on the volume, the diameter, volume mean diameter, that is, now volume means dp cube, so main thing is dp cube is there, and add with it xi, sum it, and finally what to do is take 1 upon 3, because finally we need diameter, so 3, so 3, that in a way it will get cancelled, and also this is xi by dpi, this is 1 by 3. Next is the shorter mean. Shorter mean says just that 1 upon xi by dpi. The shorter mean diameter. And now let's move to mixing. In mixing, what we find is that the power number np is power, the total power, divided by rho n cube d5. Okay, this is the power number. And if we see a graph, initially it is like this and it goes, this is the np versus the Reynolds number, and initially it is inversely proportional to Reynolds number, and finally it doesn't depend on Reynolds number. So what we can find out, that also this is a function of Reynolds number and Froude number. So Reynolds number in the case of mixing is rho and d square by mu. Okay, here instead of d, like Reynolds number is rho vd, and here is the speed rpm, which will be given in rpm, so speed, and d square upon mu, this is the Reynolds number, and the Froude number here would be denoted by n square d by g. This is a function of this, and let's put it like, for the first case will be when initially when Reynolds number is less than 0.1, or let's say it should be Reynolds number less than 10. So when Reynolds number is less than 10, then what we have is that it is inversely, np is inversely proportional to Reynolds number. That means p upon rho n cube d5 inversely proportional to rho n d square upon mu. That means power, finally we have the power is proportional to n cube d5 upon n d square n square, so d cube. Power is proportional to n square d cube. This is for lower Reynolds number less than 10, and for higher Reynolds number, let's say turbulent, we can say the np is constant. That clearly means that power number is proportional to n cube d5, because np is power upon rho n cube d5. Next we have that in the Tyler in the screening, the Tyler ratio. The Tyler ratio is that the area of the above screen. So let me make the screen. Here we have a screen and then a lower screen and various holes. So the area A1 and the area A2, whatever comes over here, the area of A1, this particular area is twice that the area of A2. That means A1 is twice of A2. That means D1 square is equal to under root of D2 square. Not square, square will be, so it will be under root. This is a relation that you must remember for Tyler ratio of the screen. And now for screen, if something is given like +5 and -10, that means plus here means something that is added, something plus quantity. So it means that retain on 5 mm screen. Okay, so here we have two screens. So this is the pore size is 10 mm, not mm, but let's say 10 something would be given here, and this is 5 mm. So this is pore size is less, the lower one. So what will happen, this will come over here. So plus of 5 mm retain and minus means pass through. This is how we denote it. Now next thing is, when we were given like oversize undersize in the flow, so what happens that in the screening, if these are like screens, there is some oversize and there is some undersize material mostly comes down, and oversized material is mostly found in the upper screens. So a way to remember it is it's just like distillation. So let's say F is feed and a D is the oversize plus B is the down bottom product. Oversize in the upper region and this is bottom, means the oversized particle, it means two particles are there. So oversized particle, how much it is coming. Okay, this is the upper product, this is the bottom product. Similarly to distillation, we can write exf is the fraction of the oversized feed particle in F, dxd plus bxb. And finally, if we need to find the effectiveness, so effectiveness 1, that means the above part effectiveness, that how much oversized material comes above, that is given by nothing but d by f into xd by xf. Now how to find this d by f? We can solve using these two and eliminate b to get d by f, which will be like this. Okay, which will be like d by f is nothing but first cross multiply in this way that xd will come down, xf will go up, and b is neglected, so b will become minus xb minus xb. This is how we can write it. And now the effectiveness 2, that is the undersize effectiveness, the oversized particle in the underflow. This is the underflow, bottom flow. So here the effectiveness will be b by f into 1 minus xb upon 1 minus xf. Here b by f could be written again like this, cross, that means this is not cross, this is a way to learn this, that xf minus xd upon xb minus xd. And finally the overall effectiveness would be overall effectiveness is E1 into E2. This is for the screening. And now let's move to the Stokes law. So in the Stokes law, it is for Stokes law means the settling, For settling, we have first the Stokes law. Stokes law formula is V is d square g rho minus rho f. This is rho of particle, rho of fluid, divided by 18 mu. And this is for the Reynolds number when Reynolds number is less than or equal to 0.1. Okay, if Reynolds number is greater, it will be then 2 mg under root 2 mg rho minus rho f. It's the same thing, but 2 mg, g is also there, 2m mass, m is mass here, mass of the particle, by cd. Cd is the drag force coefficient, and cd, a of the particle, I will tell you what it is. This area is, a of particle is like, if it's a sphere, then the area of this part, the circle, because the fluid is hitting this way, so the area would be this circle. So here let me just write it complete. For the area of circle, that is pi by 4 d square. So if I substitute mass as density into volume, so density of fluid, so 2 mg mass is density of fluid into volume of sphere, that is pi by 6 dp cube into g into rho minus rho f divided by cd into area is pi by 4 dp square into rho f. So this would be rho of particle. So rho of particle, rho will cancel out, pi cancel out, dp square dp cancel out, and 4 by 6, so this will be 1 upon 3. So ultimately 4 upon 3 would come. So let me write it completely, but you can actually do it for any particle. If it's a cylinder, then take this part as the contact area if it is flowing like this, but mostly it will be given as spherical particle. So finally 4 by 3 dg rho minus rho f upon cd rho f. This is for greater Reynolds number. Here we put a whole chart of Reynolds number. So Reynolds number 0.1, Reynolds number 10 to the power square, 10 to the power 3, and 10 raised to power 5. And we have various values of cd, so cd would come like this, and then it will go straight. So for here the cd value is 24 by re for till this point. For this point, this is 24 by re plus 0.44. For this part we have 0.44, and for last part we have 0.1. This is the range of cd. Next we have one more thing to note, is that vh is the hydrodynamic velocity, that is v of t. V of t is this one, the terminal velocity, that is d square g rho minus rho f upon 18 mu, the terminal velocity. So vh is terminal velocity to the power porosity, void edge, this void edge to the power Zaki. This is Zaki Richardson constant. So this is one formula that might come in gate or semester exam. And next formula is v of up, going up, the velocity going up, that is vt 1 minus epsilon by epsilon. Epsilon is the void edge or the particle porosity. The void edge in the bed, it's actually void edge in the bed. If we take a bed, we have void edge. Let me show you the Argon equation. Argon equation is very simple. It's Argon equation tells us that the delta P by L is 150 mu u. One way to learn is 150 like 150 रुपया देगा. Okay, 150 mu u, okay, and 1 minus epsilon whole square upon, this is phi upon d square, mu u by d square, because this is square, this is also square. Okay, this is square, so this is also square, and this is epsilon cube is there. This is the Kojani-Karman equation, and now the Burke-Plummer equation would be, this complete equation is argon. It comprises of this viscous effects. Why viscous effects? Because mu is there, and the Reynolds, the kinetic effect. Kinetic effect would be 1.75. Okay, and it is rho u square. Now it is u square, and 1 minus epsilon to the power 1 only, and down here, because this is 1, so rho dp to the power 1, rho u square by dp into phi is ferricity. Okay, this is the final formula. And one more thing to note is that for minimum fluidization velocity, delta p by L is nothing but 1 minus epsilon rho g. So it's like rho gh. If delta p is rho gl, so into 1 minus epsilon at minimum fluidization velocity. Next, now this is a revision series, so I'm moving a little fast so that we can cover everything in very less time. Okay, so now filtration. For filtration, we know that there is an alpha, the specific cake resistance. Okay, and that is delta p. Okay, this is force, so delta pc, the cake, into area. This is force. Okay, one way to remember is this force divided by mu u cv. This mu u is more in most of the equations. So mu u cv, where this c is mass upon volume, so volume should cancel, but we have written it like this so that we get volume here. Okay, so this is alpha, cake resistance, specific cake resistance, and now we have specific medium resistance. This is the medium resistance, that is delta p, and like this part we have delta pm by mu u. Okay, so these are two resistance, and finally we can write them in this equation like, because u is equal to 1 upon a dv upon dt, because volume, if you say volume upon area, this is length cube, length square, so length upon time, that is u. So finally we can write it like delta p is the total pressure difference, that is delta pc plus delta pm. And if we find out in terms of this alpha and mu, so we can find it like dt, and putting the value of u as 1 upon a dv upon dt. Okay, so I'm writing the final thing, but this is how we can actually, if you do forget, you can find out it in very simple time. You just need to know alpha m rm expressions. So after this, dt upon dv is kcv plus b. Okay, and this kc and b you can find out by putting the this way. So delta pc, like delta pc is nothing but, we know that delta pca upon mu u cv is alpha, so putting all these things over there we can find delta pc, and hence we can also find out the value of kc. But this is the major expression, and if we integrate it, we can find T upon V Kc by 2 into V plus B. Okay, in most questions B is said to be negligible, but that depends on the question. So finally a graph of T upon V would come versus V like this, where if it is not the cake resistance is not negligible, it will start at some point B, and the slope will be Kc upon 2. This is the slope. Next, now we need to see that if washing like for washing the cake filter washing, so the rate of washing, so the rate of washing is equal to the rate of filtration at the end filtrate, like let's say at the end filtration, this is the same rate. So how we can find out the time of washing? So time of washing is nothing but the volume of wash water divided by the end filtrate rate, end filtrate rate. Okay, and end filtrate rate you can find out using this uh, dt upon dv expression kcv plus b. So finally the volume of filtrate would be given to you, and so you can find out this end filtrate rate. Now for a cyclone separator we have this separation factor as v square by m rg, and it has come from like this: mv square upon r. Mv square upon r is centrifugal force divided by mg is the gravitational force. So m cancels, so v square upon rg. This is the cyclone separator, the separation factor. For now, for the next thing, if also I've let me just tell you the fluidization graph also. Okay, just I remember this, that till the fluidization, the minimum fluidization velocity, the delta p, okay, I'm talking about delta p, it would be increasing as we will increase this, but after this it attains minimum fluidization velocity, this delta p will become constant, and the length, the height of the bed, the height of the bed will be constant initially, but after fluidization it will move further. So height or the length of the bed would be constant initially, but after that it would get a peak and then increase. Now the final thing is the, if we have a roll crusher, okay, if we have a roll crusher, it is like this and like this, and now we have some distance here. Okay, let's say this distance is L. Okay, and this is R, this is also R, and some feed element is coming here of R, small r. So what we can say here is the, like, the alpha, this part join this, make a triangle. Okay, like this, make like a triangle. Okay, and finally we can find out here that cos, now this angle the angle of nip, that means this part and this part, this whole angle is alpha, that is angle of nip, and the half of the angle, because we are taking only this triangle, the half of the angle would be alpha by 2, okay, equal to r plus L by r plus r. Let me show it again. So what is happening is that we have cos, we have like this, and cos, this is alpha by 2, this is alpha by 2, so cos alpha by 2 would be this r, this part is, let me draw it again. Let me take half of the part. Okay, this part r and r. Okay, and r plus r, this is this part and this part. So what we see is this is called alpha by, this is alpha by 2, So this is 90 minus alpha by 2, so this is alpha by 2, and this part I'm talking about is r, this r plus this l, so r plus l. Okay, so the hypotenuse is r plus r, this base is r plus l, so cos alpha by 2 is nothing but cos alpha by 2 is nothing but r plus l by r plus r, and the mu is the friction coefficient, that is friction constant, this is tan alpha by 2 is mu. And finally, let me write the ball mill equation. The NC, the critical speed is 1 upon 2 pi g upon r minus r. Remember, this is r, so radius. Now one way to remember is that ball mill, this is the radius of the ball, this is the radius of ball, so ball mill. So this is the critical speed. Let me tell you just one more thing is that what happens is that we have Blake jaw crusher. In Blake jaw crusher, one is fixed, this is Blake, and the other can move here and there, while in the Dodge jaw crusher, Dodge, this is also fixed. So this is the complete revision, and I hope it was really quick and it will help you. So please subscribe to the channel. Thank you.